Okay guys, as I'm recording this, I'm starting to think there might have been a better way to do this, but we're here now, so let's just move forward. Yes, this lecture is about climate, and the first thing I want to do is make a distinction between weather and climate because sometimes those terms get confused, and I don't want you to be confused. So let's start with weather. What is weather? Well, simply put, weather is the atmospheric conditions at a certain place in time. So the temperature, the precipitation that's going on right now. So if it's cold and snowing, that's the weather, okay? And then climate is the statistical average of all that weather at a certain location over time, okay? So let me try and give you an analogy. If you think about your clothing, so weather. If you go and look in the mirror right now, what you're wearing is based on the weather. So if you were getting ready to go outside and it was cold and snowing, you'd be wearing stuff that's warm. Now, as the weather changes, you're going to change your clothes, all right? So you might have to get rid of your warm clothes for something a little more appropriate to the sunshine as it comes out. And this is going to be your weather, okay? So now the weather's changed. It was snowing, now it's sunny. Much more enjoyable. We can kind of relax and talk about climate. So climate. Climate now is, if you look in your closet and look at all of your clothes, everything you own, that is climate. So as an example, the fact that I own warm clothes for winter and cool clothes for summer is a pretty good indication that I live somewhere like New England, where it snows in the winter and gets pretty hot in the summer. All right, so that is climate, whatever your whole wardrobe looks like. So now that you guys understand that distinction, I'm going to enjoy a few more weeks of this warm weather before I actually have to wear some of my warmer clothes. And I'll see you guys back here in a bit to talk a lot more about climate. All right, guys. So hopefully the next time you're at a cocktail party and the conversation turns to climate change, you'll at least be able to educate your peers on the difference between climate and weather in case that comes up. So for this lecture, we're going to stick to climate because what you've already seen is just how intertwined the oceans and the Earth's climate are. You know, we've already discussed that movement of heat around the planet. And we've already talked about, okay, we have our rotating sphere that we live on, and we did discuss where that energy comes from, because this is all about energy movement over the planet, all right? So we've got our giant sun, and it brings all that energy to our planet. And also, this is our pretty much only source of energy on the planet. Everything we can actually trace back, it comes from the sun. So we already know that, that direct sunlight hits more towards the equator. We'll adjust here for a little bit, and then as you get to the top and bottom, it gets diffuse. All right. Well, so why do things change? And that's what we really want to talk about. Why are there differences in climate? So let's go ahead and let's zoom in here on our Earth. And let's say we're talking about sunlight. And we'll take this full brunt of the sun's energy in one shot. And the numbers here don't matter. You guys can look it up if you really want to know. But let's just say this is 100%. This is 100% of the energy that reaches Earth. Well, through a few mechanisms, there's some bounce back to the atmosphere, there's some absorption in clouds and other stuff. So for that 100%, only about 50% is absorbed by the Earth's surface. So I want you guys to remember that. 50% of the energy from the sun is absorbed by the Earth. All right. Well, as it turns out, that amount of energy isn't enough to give us a habitable planet. That amount of energy would only make global temperatures about 0 degrees Fahrenheit, so 32 degrees below freezing globally, as opposed to the balmy 60 average that we have now. So why is this? Why is it that we actually have a planet with life and it's not frozen over? Well, as it turns out, we have an atmosphere, okay? And this is what we're going to really focus on, and this is going to answer some of those questions about wind and whatnot. So this atmosphere, and what actually happens in the atmosphere is the Earth itself radiates energy. and it radiates energy back to space, okay? But some of that energy bounces back. So it hits the atmosphere and comes back. It actually can't escape. You guys may have heard of this, all right? And it's something called the greenhouse effect. And the reason it's called the greenhouse effect is it works like a greenhouse. So in a greenhouse, you have the sun's waves, light coming into the greenhouse. It gets absorbed by the plants and by the ground. And then what happens is all that earth and plant life emit a different wavelength of energy. The sun has these short waves that come in as visible sunlight, and then the infrared that comes up, different wavelength of energy, can't escape the glass. So short waves can make it in, but those longer waves can't make it out, and they bounce back. And it ends up, it could be in the dead of winter, as long as you have sunshine, inside this greenhouse you have warmth and life. And this is the reason we have tomatoes in February from Maine, all right? And the atmosphere works like that. So we don't have glass, okay? But we have stuff in the atmosphere. And you may have heard of greenhouse gases, and we're going to talk about those and all of the gases in the atmosphere. Now, the important thing about the greenhouse effect is this is not a bad thing, all right? This is a wonderful thing. In stable times, the greenhouse effect is what makes the Earth habitable. It's what makes it nice. Again, that average 60 degrees Fahrenheit vice 0 degrees Fahrenheit. So let's just talk about the greenhouse effect before we talk about any changes. And let's see what's in the atmosphere that does this. All right, so we have our atmosphere, but the first thing to note is this is a massive exaggeration. You know, one thing I want you guys to get is scale. So let's get rid of that, and let's talk about this really thin little atmosphere on the Earth. In fact, just to give you an idea of how thin it is, it's about 100 kilometers, which is about 60 miles. So if you look real close here in Florida, I'm going to put a little line here. And I don't know if you can barely see that. You might have to zoom in. So 60 miles, 100 kilometers, is about half the width of Florida at its widest part. It's about that. So if I take that little bar and I move it up here to the atmosphere, that is as thick as the atmosphere is on the planet. Not only that, but all these processes that we're talking about, all these winds, all these circulation cells, all this stuff that's happening in the atmosphere happens in the lower atmosphere, which is only about 10 kilometers high, or 6 miles. So here in Rhode Island, that's about from, the Warwick campus to TF Green, all right? It's not that far. So really, really thin around the Earth. Okay. So anyhow, we're in the atmosphere, so what is it? We don't have glass. What is inside here that gives us this insulation or creates this coating around the Earth? So if we break it up, again, it is now going to be the volume of gases, water vapor, and particles. All right, that is the atmosphere. So these gases taken as a whole, so this is 100%. The first thing is, and I want you guys to know this, I'm going to say this is 4 main things that I want you to know. So the first one is nitrogen, okay? About 78% of the atmosphere, or most of it, most of the air we breathe is nitrogen, which is inert, which means it doesn't really do anything. We inhale it, we exhale it, not a whole lot happens. And then about 21% is oxygen, all right? So that's the stuff you guys already know. We like oxygen. That's our favorite. That's what we use for metabolism. That's what we use for life, for living. And we'll talk more about that when we get into more metabolism. And then water vapor. Again, this is oceanography. Water's really important, and that varies. And that can be up to 4%. Usually on the surface of the planet, it varies between 1% and 4%. And that's where that, days feel more humid than others. When you say 100% humidity, that means about 4% water, okay? And then what we're left with is this other. All right, so those are the ones I want you to know. Nitrogen's important, oxygen's important, water vapor's important, and other. And if you get some of these other ones and you remember them, that's great. So other, again, this is a lot of things, but primarily the first one is it's mostly argon. And argon is a noble gas. Again, it's something that doesn't do a whole lot, at least for us and for our discussion here. So that's fine. And then even smaller amount is methane, neon, and carbon dioxide. And I know you guys are familiar with carbon dioxide, and we're definitely going to talk about that more. Methane you may have heard of. Neon I'm sure you've heard of, but again, that's one of those noble gases. it's not going to be real important to our discussion. So this is what makes up the atmosphere. This is what makes up the air that we breathe, okay? And as we're talking about greenhouse gases, those are things like carbon dioxide, methane, and water. And there's certain reasons for this, and I'll show you that in a minute, but these gases have particular properties that actually make them absorb that energy coming off Earth. They get real excited and they hold it in and then they spit it back down to Earth, all right? And that keeps that cycle going. And again, it keeps things nice. All right, so again, all of this stuff, the atmosphere, this is all air. So this answers that first question. This is air. This is the stuff we breathe. Again, we need oxygen, and we're going to talk a lot about carbon dioxide, a little bit about methane. And then I asked you, what is air? And we can see constituents, but air is a mass, right? So we said wind is moving air. We talked about currents. Currents are movement of mass, and air has mass. And I've used that term mass an awful lot already without really getting into it too much, so I just want to touch on it a little bit. All right, so mass. Maybe you guys have seen this before. This is the periodic table of elements. Every atom that we're aware of and many that we've created are on here. If you're familiar with it, great. If you're not, there's only a couple things I want you guys to pull out of here. And mainly where things are on the table and how much mass they have, right? How much they weigh on Earth. Remember, we talked about weight is that mass times the acceleration of gravity. And you can see things here we've already talked about. So we've got carbon and nitrogen. Over here is your neon and argon that we just spoke about. Hydrogen up here in the corner. And they all have different masses. And the masses get bigger as you kind of go back and forth on the table. And what's really important about this, just one thing I want to show you guys is, so these atoms, so let's use for an example, where's my, I'm going to find something that we know. So here's iron, right, this Fe. Well, iron as an atom isn't really iron, okay? It's just a ball of neutrons and protons with some electrons on the outside. All of these, that's all they are, some neutrons and protons with electrons on the outside. What makes them special is the way they interact with either themselves or other atoms, other elements on the periodic table. And that's, again, what makes these greenhouse gases so special. So let's take, for an example, because I am going to ask you this in your next homework, how to do this. Let's look at methane, all right? So we said methane is CH4. So it's a carbon and 4 hydrogens. So here's carbon right here, and here's hydrogen. So if I were to ask you, hey, what's the atomic mass of methane? You would have to find the atomic mass of carbon, which is about 12, and the atomic mass of hydrogen, which is about 1.01. And yes, they have units as well, and those are atomic mass units. If you want to ask questions about exactly what that is, I'm happy to go into it, but it's not necessary for us right now. Just don't forget them. So if I do this, I'm going to have 1 carbon, and I'm going to have 4 hydrogens. So I'm going to add those up, and I'm going to get a mass, all right? And what does that give me? About 12 plus 4, right? 16 is the atomic mass of methane. Now, the other thing is, like I said, it is, along with carbon dioxide and water, they are greenhouse gases. And the reason they're greenhouse gases is those bonds that they share, those hydrogens attached to that carbon, they're stuck on there pretty good. I mean, you couldn't rip them off, but they're not incredibly strong. It's a single bond between a single pair of electrons or a single electron. And what happens is when that radiation comes back off of Earth and hits these molecules, they start to vibrate. They get excited. The atoms start to move around, and they hold onto that energy. And then when they can't hold onto it anymore, they spit it back at Earth. And things like nitrogen, right, most of the atmosphere, that's 78%, that actually is a really tight bond. That's 2 nitrogen atoms stuck together in 3 places and really held on tight. So they don't get very excited. They're pretty cool. They just chill out. They get hit with infrared radiation, and they don't care. So it is those molecules that, again, water, carbon dioxide, methane, that can absorb that radiation, excite themselves, and then spit it back out. And that is why we have a habitable planet. So that is also why when you put too much of this stuff in the atmosphere, too much carbon dioxide and too much methane, well, that's too much radiation coming back to Earth. And that's where we have this runaway greenhouse effect that you may have heard of, and global temperatures can start to heat up. Anyhow, I'm not going to belabor climate change at this point. I just want you guys to know the fundamentals of climate so that you can talk about this. So the reason this is important is because Earth has some natural variations that aren't dependent on this influx of greenhouse gases. All right? And what I mean by that is, okay, we go back to this picture of the incoming radiation from the sun, where I said about 50% of it is absorbed by Earth. Some of it gets radiated back, hits those greenhouse gases, and comes back down. Great. Well, the thing is, this 100% isn't constant. That 100% varies between actual numbers, like actual amounts of energy. And that's where we get some natural variations. And those variations are something called Milankovitch cycles. And that's what we're going to talk about now, right? On a large scale, the energy from the sun varies through time. And through geologic time, this actually happens pretty quickly. We don't notice it much as, little dinky humans with a little short lifespan, but it actually happens pretty quickly. And there are three of these, all right? Eccentricity, obliquity, and precession. And we're going to go through each one of these. And this is now where we're getting into when I asked you, hey, where do seasons come from and where do ice ages come from, right? Climate change. So the first one I'm going to tackle is actually this obliquity. So we're going to talk about seasons, all right, and then we're going to move into the other two and talk about bigger climate issues. So this is obliquity just means the tilt of the Earth. The Earth is on a tilt. So if I take the Earth, we've been looking at this with the sun. Well, actually, the sun hits it at an angle, all right? So if we're going to, swap this, I've shown you this picture before, but I hadn't tilted the Earth. So what's actually going on, you guys may know this already, is because the sun hits the Earth at an angle, so again, this red line is still that area of intense sunlight, and it gets more diffuse as you go top and bottom. But because it's tilted, this is why we have seasons. So up here in the northern hemisphere where we are, when we're tilted away from the sun, we're getting that diffuse sunlight. So it's not that we're closer or further away. In fact, in our winter, we're closer to the sun. I'll show you that in a minute. But anyhow, we're tilted away. So as the Earth spins, we get more diffuse sunlight. And then at the same time, they have their summer in the southern hemisphere. Well, as you know, we sit here and wait, and we're starting to approach winter now. 6 months later, we're on the other side of the sun, and we're tilted towards the sun in the northern hemisphere, and we have our summer. And that's where the seasons come from. This is why we have summers and winters. So you guys can see here, big picture, we start on one side in the summer, the Earth stays tilted the same way all the way around, and stops back again, and we go through all of the seasons. And so I guess we're probably about, here-ish right now, right? Approaching winter. Well, so that's right there. We've answered why we have seasons. So now let's move into why there are changes. Why does the climate change? So obliquity isn't always the same, all right? So the Earth is tilted, but you'll see that tilt varies, not a whole lot, but between about 22.1 and 24.5 degrees, and it wobbles back and forth. And it wobbles on a 41,000-year time scale. Now, that seems like a long time, but really, for Earth, that's really, really short. I mean, humans have seen a lot of these as far as how long we've been on the planet, and we haven't been here very long. So what that means is with our big sun and that energy coming, right, our most intense beam varies a little bit, and that diffuse beam varies a little bit. So a little bit of the sun's energy coming into the planet, it's going to make some subtle changes, all right? And that is obliquity. Now the next thing is, I showed you the sun going around, or the Earth going around the sun. Well, that doesn't happen in a circle. You guys may know this, it happens in an ellipse, okay? So it's sort of egg-shaped. So here's our Earth, and it travels around the sun in a bit of an egg shape, and over here it's closer than it is here. In fact, if you looked at it from space, you wouldn't notice a huge difference. But looking at it here, at our closest point, we're about 147 million kilometers away. And at our furthest point, we're at about 152 million kilometers. So a difference of about 5 million kilometers. Again, like I said, if you looked at this from space, you wouldn't notice much, but it makes a bit of a difference. And I also told you that in the northern hemisphere, our summer is actually when we are further away. So the distance from the sun has less of an effect than that tilt. Okay, so this happens, but it changes, all right? It changes a bit. So if you look now at this ellipse, it's going to wobble, all right? And it's going to go between a perfect circle, and this is the green line is extremely exaggerated, but ellipse. And you can see just by looking at this, what that means is the Earth's distance from the sun varies quite a bit as this moves around. And this is something called eccentricity. And it varies between 0 and 0.06. Don't worry about those numbers too much. That just has to do with the way we define an ellipse. 0 is a perfect circle, and 0.06 is very, very slightly more egg-shaped. And this cycle happens every 100,000 years. Again, a bit more than obliquity, but still pretty quick. The third one we're going to talk about is this precession. And this one's a little weird, and there's a couple different kinds of precession. And what this really means is, yes, the Earth is at an angle, but that angle changes, all right? So sometimes we're pointed here, and sometimes we're pointed here. And it's a bit of a wobble, all right? So what ends up happening is we point the North Star. Well, we don't exactly always point the North Star. The best way I can think of to explain this is if you guys have ever played with a top, right? As it starts to slow down and wobble a bit, that is sort of like precession. And that just, again, that's going to change where we're tilted towards the sun and away from. It combines anyhow. We also have something called a orbital precession. And those two combined, so actually you look at this, I already showed you this figure, when our summers over here were angled towards the sun. But because that axis shifts, well, I guess half of that, so as that time goes around, and we end up over here towards the sun. So in space, we end up at a different spot towards the sun. And again, all of these combined are really what make these changes happen. And we get, again, this wobble with sort of our ellipse. And again, this is greatly exaggerated, but it does move a bit. So you put all of these together, your eccentricity, obliquity, and precession, and you get changes in the intensity of the sun's energy. And I already told you guys the cycles. You do need to know these, all right? So, top of the line here is more sun energy, and bottom is less. So between eccentricity, obliquity, and precession, both axis and of orbit. Well, these get stacked on top of each other, all right? And they look a little something like this. So up here on the top, we have precession, again, obliquity, eccentricity, these same sort of figures I showed you here. And you combine them all into something called solar forcing. And this figure is just showing you solar forcing from now all the way back to 1,000 years ago, or 1,000,000 years ago. And what you end up with is something like this, where our global temperatures are hot to cold, and they cycle. So right now we're here, we're warm. Well, cold, warm, cold, do you see what I'm doing? So each one of these dips, 1, 2, 3, 4, 5, 6, there's a lot of them, are ice ages, all right? So every time that dips, we have an ice age. So this is that normal change in the Earth's climate. And again, this could be a cocktail party conversation. Sure, we have normal changes, but that's not what we're seeing now. And actually, we get a little further into the semester, and I'm going to give you guys some exact numbers to show you just how far we're moving out of this pattern, right? Away from this. We have a very established pattern for solar forcing, and we're outside of it. So anyhow, we've now answered, what were the first ones? What is air? What is wind? Where do seasons come from? Where do ice ages come from? We now understand how the ocean is tied in with climate. We understand why climate changes, the greenhouse effect, major ocean currents, all right? And you can see where I'm going here. We're actually finished with Module 1. So the first quarter of the semester is over. And we're going to move now into our next environment. So this is finishing up with that pelagic open ocean environment. And look at everything we covered. We made it all the way out into space for hundreds of thousands of years just talking about oceanography. So anyhow, go back, finish up that last homework, or that second homework for the module. Or if you guys plan on taking the exam, get ready for that. Redo the readings. I always say this, come to my office hours if you have questions, send me emails, and I'll see you guys in Module 2.